Now let's do an example to sort of hammer this home. You may want to pause the recording here to read this, but basically what we have is sulfur. S8, that's the form of sulfur, solid sulfur on these conditions, exists in two phases. We got a rhombic phase below 95, and we got a monoclinic above 95.5, and this is at 1 bar at pressure. We have the density of the rhombic phase and the density of the monoclinic phase. We have the entropy, so let me call this the partial molar entropy change. Going from rhombic to monoclinic is that. Calculate the pressure necessary to make rhombic sulfur stable at 100 degrees. All right, so just let's draw the piece of the phase diagram that this problem is referring to. This is the pressure axis, and this is the temperature axis. We're saying at 1 bar and at 95.5, that's the phase transition. Why is that? Because below it you get one phase and above it you get another phase. So that's a point along the phase boundary, and just let's draw this. Okay, there's a boundary. So over here below 95 at 1 bar you have the rhombic, and here above 95 you have the monoclinic. So at 1 bar, if you now go up to say 100 degrees C, at 1 bar you'll be in the monoclinic. What you want to do is to increase the pressure, so now you're at the rhombic. So the rhombic will be the stable phase. So we want to have a pressure change to bring this point at 1 bar at 100 degrees from the monoclinic up into the rhombic phase. So what should that pressure difference be? Well, we know from the Clapeyron equation that dP dt is some quantity, or let's use finite differences. So delta P will be those quantities, which we know what they are, times delta T. So we now have the delta T, we can calculate delta P. What's inside there? Well, remember that was how the partial molar volume changes in going from one phase to another, divided by the partial molar volume change, partial molar entropy change divided by the partial molar volume change. So that's the proportionality constant between pressure and temperature. Essentially it's the slope of this line, just as we said. So let's get busy and calculate it. This we were already given in the problem as 1 joule per mole Kelvin. How are we going to figure out how the volume changes when you go through that phase transition? And just to be clear, the phase transition we're looking at is S8. That's the form of sulfur, 8 sulfur atoms in a molecule that's in the rhombic phase, goes to S8 in the monoclinic phase. So that refers to the partial molar volume or partial molar entropy change. This refers to the partial molar volume change. What we can do, if we can figure out what the partial molar volume is of both phases, we take the final phase, that, subtract off that, and that will give us the partial molar volume. So what are we given in the problem? We're giving densities. Oh, that's interesting. So that's the volume occupied by a gram, but the partial molar volume be the volume occupied by a mole. Oh, okay, so I think we got it. Again, V2, say this will be correspond to the monoclinic. So the 2 will correspond to the monoclinic. That is equal to 1 over the density, which is 1.96 gram per centimeter. So this gives you how many centimeter cubed a gram occupies. And let's convert that to SI units. So let's multiply this by 10 to the minus 6, a meter cubed per centimeter cubed. And it'll be clear later on why we want SI units. And now we got to convert the grams of sulfur to moles of sulfur. And that's S8 is 256 gram per mole. So this comes out to be 1.31 times 10 to the minus 4th meter cubed per mole. That's the partial molar volume of the monoclinic phase. Let's do that for the rhombic phase. That'll be 1 over the density of the rhombic phase. There's a density of the rhombic phase is there. We use the density of the monoclinic phase already. This would be 1 over 2.07 gram per centimeter cubed. We'll multiply this by 10 to the minus 6 centimeter cubed. Oh, there you go again. Sound like Ronald Reagan. There you go again. Ronald Reagan was president in 1980 and 1988. He was also an actor. We have meter cubed per centimeter cubed. Convert to SI units. Get rid of that gram, convert it to mole, 256 gram per mole. So the partial molar volume of sulfur in the rhombic phase is 1.24 times 10 to the minus fourth meter cubed per mole. The change in partial molar volume will be the final, which is monoclinic. We're looking at the transition from rhombic to monoclinic, so here's the final, minus the initial. That's the rhombic phase. So it's 1.31 times 10 to the minus fourth minus 1.24 times 10 to the minus fourth. So that comes out to be 6.94 times 10 to the minus sixth meter cubed per mole. So that's a change in partial molar volume. So, as we said, delta P, we're converting from infinitesimal to finite changes, which is essentially assuming that that phase boundary line is linear over delta T. That is equal to delta S bar over delta V bar. Delta S bar, given the problem, 1.00 joule per mole Kelvin. Delta V is, we just calculate what that is, 6.94 times 10 to the minus 6 meter cubed per mole. And that comes out to be 1.12 times 10 to the fifth joule per meter cubed Kelvin. So there's a proportionality constant between delta P and delta T. So the change in pressure we have to have in order to make rhombic the stable phase at 100 degrees will be 1.12 times 10 to the fifth joule per meter cubed Kelvin. Delta T, we want to go to 100, and we're starting at 95.5. And earlier discussion, delta C is the same as delta K. So this is equal to 5.0 times 10 to the fifth joule per meter cubed. The SI unit of pressure is the Pascal. Let's just figure out in fundamental units what the unit of pressure is. Pressure is defined as force per unit area, and force is mass times acceleration over area, and this will be the mass times, say, delta x over delta t squared divided by area. So let's just put that in, mass times length divided by area would be length squared, and this would be the units, SI units of time squared. And so let's actually continue on here. Let's put in the SI units. Well, let's simplify that a little bit first. That will be mass, one of the lengths cancels out, over length times time unit squared. Let's put in SI units. SI unit of mass is kilogram. SI unit of length is meter. SI unit of time is second squared. And this is called, this unit, this SI unit is called a Pascal. Now let's go back up here. Let's see, our units we got for delta P will be joule per meter cubed. Is that a Pascal? Yeah, I think it is. But just to show you, a joule per meter cubed, a joule is a kilogram meter per second squared, and we have the meter cubed here. That's just equal to a kilogram per meter second squared. Oh, look, so a joule per meter cubed is the SI unit of pressure, which is Pascal. All right, one further thing is that 1 bar is defined as, that's not the SI unit of pressure. The SI unit of pressure is Pascal. 1 bar is defined as 10 to the fifth Pascal. Why are we doing this? Well, we started at 1 bar, and we want to know what the pressure will be. And I didn't really say that. Let me just stick that in here, in bar, when you go to the 100 degrees. We have delta P is 5.05 times 10 to the fifth Pascal. So we have delta P, we calculated, was 5.03 times 10 to the fifth, we said joule per meter cubed, and that's equal to 5.03 times 10 to the fifth Pascal. And that's generally true. I mean, if you use SI units throughout, then whatever quantity you're calculating will have the SI unit. And this is equal to, we have to multiply, because we want it in bar, that's what we're asked to calculate in the problem, 10 to the fifth, so sorry, 1 bar over 10 to the fifth Pascal. I just love the eraser function. So this is 5.03 bar. All right, so delta P was P final, that's what we want, minus P initial. So the final pressure is the initial pressure plus delta P. The problem, the initial pressure was 1 bar, and the delta is 5 bar. So the final pressure you have to be is 6 bar. What does this calculation do? Well, it says that now you have to go up to 6 bar in order for the rhombic phase to be stable at 100 degrees C. Kind of neat. We calculated those. That's what physical chemists really get excited about, calculating things like that.